afternoon, dear students. My name is Nigar Çarşıbaşı, and in the scope of General Chemistry Chem 102 course, today we are going to discuss acids and bases. Here is an outline of the presentation. First of all, we are going to discuss the general properties of acids and bases. We are going to classify acids and look at their definitions in terms of Arrhenius and Bronsted acid and bases. We are going to consider neutralization and ionizations of acids and bases. Then we will discuss the strength of acids, how strong acids and weak acids or bases can be classified, and differences between their ionization power. And finally, we will measure the acidity and the pH concept. Let's start with the properties of acids first. So acids and bases are also widely used in everyday life. Acids have a sour taste. For instance, vinegar owes its taste to acetic acid. Citrus fruits also contain citric acid. Acids cause color changes in plant dyes. They turn blue litmus paper to red, and they react with certain metals to produce hydrogen gas. For instance, in this demonstration, in this figure, you can observe that in the tube we have hydrochloric acid, and magnesium metal is inserted into the tube. And you can observe here the gas formation, the hydrogen gas formation in terms of bubbles that is on top of the layer. Acids can also react with carbonates and bicarbonates to produce carbon dioxide gas, as in here you can see hydrogen chloride or hydrochloric acid in water reacts with calcium carbonate solid, and in turn carbon dioxide gas is liberated. Aqueous solutions of acids conduct electricity. They are electrolytes because they form ions in solution. Now let's look at the properties of bases. Bases have a bitter taste. They feel slippery. For instance, you may have witnessed the slippery of soaps. Many soaps contain bases. And they cause color changes in plant dyes. They turn red litmus paper to blue. And also similarly, aqueous-based solutions conduct electricity because they form ions in the solution. Some examples of bases can be seen here. This is ammonia, which is a base which exhibits basic characteristic when dissolved in water, let's say. And this is hydroxide ion. So now we will examine and investigate how we can classify whether one substance is an acid or a base. So the first definition is the Arrhenius definition. Arrhenius is a scientist, and according to his definition, Arrhenius acid is a substance that produces H+ proton or hydronium in water. Okay, consider hydrogen chloride again. If we take hydrogen chloride and dissolve in water, we will observe that hydrogen chloride will donate its proton to water, and in turn hydronium ion and chlorine ions will be formed. As a result, hydrogen chloride here shows acidic character. This is an acid, Arrhenius acid, since it produces hydrogen or hydronium in water. On the other hand, Arrhenius base, like the case of ammonia, is a substance that produces OH- in water. Ammonia, when dissolved in water, will produce OH- hydroxide ions in solution. That is why it is classified as an Arrhenius base. So, whether the presence of hydrogen plus or the presence of hydroxide will classify that substance to be an Arrhenius acid or a base. So what is hydronium ion? Actually, it is just a hydrated proton. If proton is surrounded by water molecules, if it is transferred to water, we call it as the hydronium ion. It's nothing but a hydrated proton. So the Arrhenius definition of acids and bases, however, are limited. Why? Because it applies only to aqueous solutions. What if we don't have a solution? Can't a substance exhibit an acidic or a basic character even if it is not in aqueous solution? So a broader definition comes from Bronsted. He is also a scientist, and according to Bronsted definition, a Bronsted acid is a proton donor and a Bronsted base is a proton acceptor. So here in this case we see that we talk about only proton, whether it is accepted or donated. So a Bronsted acid, according to this definition, must contain at least one ionizable proton. Now let's see, according to Bronsted definition, how HCl or hydrochloric acid is an acid. So hydrochloric acid, as we saw, donates one proton to water, and in turn hydronium ion is formed in the solution. And that is why it's a Bronsted acid, because it donates a proton. And this proton is accepted by water, as you see. So water shows basic character in here. It's a Bronsted base, since it accepts a proton, combines the proton with water, and hydronium ion is produced. So coming to the electrolytic properties, electrolytes are the substances that conduct electricity. As a result, we must have ions in the environment. So strong electrolytes, 100% dissociation occurs in this case. The molecule completely converted to ions, corresponding ions. For instance, sodium chloride salt. When you dissolve sodium chloride, table salt, in water, it will completely convert it to sodium plus and chlorine minus, and it's a strong electrolyte. However, a weak electrolyte does not conduct electricity in a considerable extent. It's a weak electrolyte, and its dissociation is not complete. It's not 100%. For instance, acetic acid can be given as an example to this one. Acetic acid dissociation is not complete. So there is a reversible reaction taking place in here. So it's two-way reaction. So the ions formed can be back converted to the molecule, and the ion formation is in a low extent. So strong acids are also strong electrolytes because their dissociation is completed. However, weak acids are also weak electrolytes because their dissociation is not considerable. Similarly, strong bases are strong electrolytes and weak bases are weak electrolytes. They don't dissociate appreciably. Acids can be also classified to be monoprotic, diprotic, and triprotic acids from the aspect of the number of ionizable proton that is present in their structure. For instance, these are monoprotic acids: hydrogen chloride, hydrochloric acid, nitric acid, and acetic acid, because they have only one ionizable proton. So the first two are strong electrolytes and strong acids, and the third one is a weak electrolyte and a weak acid. Diprotic acids contain two ionizable proton, and initially the first proton is ionized. So this is a strong step, and that's why sulfuric acid is also a strong acid. However, ionization of the second proton involves a reversible reaction, which in this case corresponds to a weak electrolyte and weak acid property. Triprotic acid, the best example can be given as phosphoric acid in this case. It has three ionizable protons in its structure, and all the three steps are involved as reversible steps, and that's why phosphoric acid is a weak electrolyte as well as a weak acid. In this table, you can observe some common strong and weak acids that we mentioned so far, like hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, perchloric acid. These are all some type of common strong acids. On the other hand, hydrofluoric acid, nitrous acid, phosphoric acid, and acetic acid can be given as example to weak acids. Okay, coming back to the Bronsted acid-base definition. Looking at the ammonia example this time, which is a weak base. So, solving ammonia in water, dissolving in water, what happens? Let's observe this reaction. Ammonia combined with water. Ammonia receives one proton from water, as you see, and becomes ammonium ion, and water is converted to hydroxide ion. In this case, ammonia is a Bronsted base because it accepts a proton, H+. And water is a proton donor, then it can be regarded to be a Bronsted acid. Ammonia is a weak electrolyte, therefore it's a weak base, and we can give examples to strong electrolytes and strong bases like sodium hydroxide and barium hydroxide. These are strong bases, on the other hand. So there is an important point at this step. We see that water can behave both like an acid and a base. So what do we call such substances which exhibit both acidic and basic character? They are called amphoteric substances. So as you see, here water behaved like an acid. However, in the case of HCl, it behaved like a base. That's why it exhibits both character, like acid with a base, base with an acid. We call such substances as amphoteric substances. Now coming to the acid-base neutralization concept, when we mix acid and a base, the neutralization reaction takes place, and in the end salt and water are formed. The best known example is the neutralization reaction between hydrochloric acid and sodium hydroxide, which are both strong acid and strong base. In the end, sodium chloride salt, which is also soluble in water, is formed, and also water molecule is formed. So since these are both strong electrolytes, they are completely ionized in water. And in here, the molecular equation involves dissociating both the acid and the base in the form of ions. Sodium chloride is also soluble in water. That's why we also express it in the form of ions. And cancelling the ions appearing on both sides, we obtain the net ionic equation, nothing but the formation of water molecule actually. Coming to the neutralization reaction involving a weak electrolyte. For instance, we can neutralize a weak acid with a strong base. Now what happens? What is the difference? In the case of a weak acid like hydrocyanic acid, for instance, so since this is a weak acid, its ionization is not appreciable. That is why we shouldn't express it in the form of ions, but it is like molecular, keeps its molecular structure. So this is a strong base. We express it like ions, and sodium cyanide salt is also soluble in water like all sodium-containing salts, because we know that all alkali metal ion salts are soluble in water. So we can also separate sodium cyanide salt as sodium and cyanide ions, and in the end we end up with the net ionic reaction. Okay, some neutralization reactions can produce a gas also if certain salts like carbonates, bicarbonates, sulfides react with acids to form a gaseous product. We can give example, for instance, hydrochloric acid reacting with sodium carbonate in here. In the end, so sodium carbonate behaves like a base here. In the end, sodium chloride salt, water plus carbon dioxide gas is formed. There are other examples. Similar reactions can be given involving gas production. How about the acid-base property of water? So water, as you see, is associated with hydrogen and hydroxide ions if dissolved, if it is expressed in ion formation. So this is actually autoionization of water. You can also visualize it like that. So two molecules of water can be combined to form hydronium ion and hydroxide ion. So these are actually similar expressions. We can see here that the acid, for instance, one molecule of water takes one proton from the other water molecule and it becomes hydronium plus. That is why it is like an acid here. And that is the other one is behaving like a base. And these are the conjugate acid and base pairs, as you see. What is the equilibrium constant for the autoionization of water? For all reversible equilibrium reactions, as you know from previous lecture, we can write the equilibrium constant expression. So it may be expressed either like that, hydronium ion concentration, hydroxide ion concentration, or simply you can also express it with hydrogen plus and OH minus concentration. We also term this equilibrium constant value as the ion product of water and designated by Kw. So Kw is called the ion product constant, which is the product of the molar concentrations of H plus and OH minus at a particular temperature. For instance, for pure water at 25 degrees Celsius, this value is measured to be hydrogen concentration 10 to the minus 7 molar and the hydroxide ion concentration 10 to the minus 7. They are equal, and thus the ion product value for water at 25 degrees Celsius is known to be 10 to the minus 14. Then at this point we can regard a solution to be whether neutral, acidic or basic according to the concentrations of H plus and OH minus. If both concentrations are equal, then these two solutions are neutral. If hydrogen ion concentrations exceed the OH minus concentration, then it is an acidic solution. If the reverse is valid, then that's a basic solution then. So pH is a measure of acidity, and pH is defined to be negative of the logarithm of the hydrogen plus concentration. So if a solution is neutral, then both concentrations are equal to 10 to the minus 7. If you plug in here, then that will be pH is equal to 7 for neutral solutions. In the case of acidic solutions, then H plus concentration will be higher than 10 to the minus 7, but since this is minus the logarithm, then the pH value will be lower than 7. So as you see, as the pH value is increasing, H plus concentration is decreasing. Because there is an inverse relation, right? Okay, here are some other important relationships. And here are some pHs of some common fluids. For instance, our stomach, the gastric juice in our stomach corresponds to a pH value of around 1 to 2. So it is highly acidic. And if you go down, lemon juice, grapefruit juice, orange juice, you see that the pH values are increasing. So acidic property is decreasing actually. And when you come to the pure water, its pH value is around 7. And you see that blood is near neutral, but it is a little bit basic, and it goes on like this. For instance, ammonia pH value corresponds to 11, which actually shows that it is basic. So as we define pH value, you can also define the pOH value similarly in the same fashion. So it is minus the logarithm of, this time, the OH minus concentration. As a result, if you plug in the ion product of water, you will obtain this useful relation, which is relating pH to pOH. So if you know one of them, then you can find out the other one because their summation is 14. So this is pH meter. You can experimentally record and see the pH value of a solution just by inserting the probe in here, okay, into the solution, and you are going to read the pH value here. You can also compare with the calculational value when you obtain from the minus logarithm of H plus, and you can compare both values. So let's look at in molecular detail about the strong and weak acids, how their ionizations are different. So this is the case of hydrochloric acid, which is a strong acid, and this is an example of a weak acid, which is hydrofluoric acid. we will see that at the beginning, before ionization, we have only hydrochloric acid, molecular hydrochloric acid, but when it is dissolved in water, we will obtain that at equilibrium, we will no longer have molecular hydrochloric acid, but all of them will be converted into ions. However, in the case of a weak acid, we will see that the ionization is not a considerable extent. The H plus and F minus concentrations are much less than the initial acid concentration. That is why for weak acids we talk about an equilibrium expression, which is the acid ionization constant Ka. For a general acid like this, Ha dissolved in water producing hydronium ion and A- ion, we can write the Ka value as the ion concentrations divided by Ha. So as you may guess, for weak acids, this Ka value will be much less than 1. As the Ka value increases, the acidic strength, although it's a weak acid, is a little bit increases. Okay, at this point, I have a demonstration for you about the dissociation of a strong and weak acid. So we said that the dissociation or the strength of an acid depends on how much extent does the acid ionize in water. So if it ionizes completely, in the case of a strong acid, then it is strong electrolyte as well. For instance, consider a general acid which is Ha that is dissolved in water. What happens? One H proton is donated to water, and in turn hydronium ion and A- will be formed. And in the case of a strong acid, this is almost complete. This reaction is almost complete. As you see, all the initial amount of acid is converted to A- and hydronium ion. So in the end, we expect no longer to have the Ha, but all of it will be converted to the proton, which is hydronium ion also. So this is the case of a strong acid. Similarly, let's discuss what happens when we have a weak acid this time. In the case of a weak acid, then this will be just another version. Now it will be just the dissociation will not be completed, will not be going in a considerable extent. Again, there may be some production of hydronium ion, but it will be converted back to form the Ha, the initial molecule. That is why the concentration of hydronium ion will be much less. Now let's examine what happens at the molecular level. So when you add a strong acid to water, what happens? Let's see at the molecular level. So this is strong acid that is poured into water molecules. These are water molecules, and now my strong acid like Ha is inserted. So as soon as they enter, you see that hydronium ion formation is continuing, and all the acid is converted to hydronium ion and also the anion A-. There is no longer Ha, and the Ka value is much higher than 1, as you see. However, in the case of a weak acid, let's look at what happens at the molecular level. This time, the acid dissociation will be so much limited. These are water molecules again. We inserted our weak acid. Although some hydronium ions form, they can back convert to Ha, which is the weak acid. So we observe little concentration of H plus or hydronium ion in the case of a weak acid. And that is why their Ka values are much less than 1. So this is another demonstration with a comparison of hydrochloric acid and hydrofluoric acid. So hydrochloric acid is a strong acid and hydrofluoric acid is a weak acid example. Now we will examine what happens when we dissolve them in water. Okay, let's begin with hydrochloric acid first. which is the strong acid, and examine what happens if we just introduce some strong acid in the form of hydrochloric acid into water. So when hydrochloric acid is inserted into water, we will immediately see that all the hydrochloric acid molecules will be converted to corresponding H plus and Cl minus, and no longer we will have HCl molecules in solution. That is why it is called to be a strong acid. However, in the case of a weak acid, which is hydrofluoric acid, we will observe that limited conversion will be maintained, and that is a weak acid in the case of a weak acid. Okay, in this table you can see some ionization constants of some weak acid. As you see, they are on the order of 10 to the minus 4, 10 to the minus 10, much less than 1. That is why we can talk about a percent ionization, which is how much ionized acid concentration we'll have at equilibrium compared to the initial concentration of acid. So for strong acids, percent ionization is 100%. However, in the case of weak acid or a weak base, this value drops dramatically. And here are some ionization constants for some weak bases. And this is another demonstration showing a strong base, which is sodium hydroxide, comparing with a weak base, which is ammonia. And look at the ionizations of these two bases. First of all, we can start with sodium hydroxide, and then we can go on with ammonia. Let's begin with sodium hydroxide base. So we are adding solid sodium hydroxide into water, and immediately it will dissolve in water. Look at the molecular level, what happens. So sodium hydroxide molecules are surrounded by water molecules, and as the reaction proceeds, as the dissociation continues, we'll see that sodium hydroxide concentration drops while sodium plus and OH minus concentrations are increased. So in the end, all of the sodium hydroxide should be converted to sodium plus and OH minus, since this is a strong electrolyte, and we will observe that it is also a strong base. Actually, what happens when the hydroxide ions are formed, these are combined with the H plus of the water, and in the end water molecules are formed. So you see that finally at equilibrium we will no longer have any sodium hydroxide base. All of it will be converted to sodium plus and OH minus. Now let's look at the ammonia example, which is a weak base. If we add ammonia, if we dissolve ammonia in water, what happens? As soon as we add ammonia to water molecules, it tries to again dissociate. What happens? As you see here, one proton will be donated to ammonia and ammonium ion will be formed. But this ammonium ion can be combined with hydroxide and can be converted back to the ammonia. Since this is a weak base, it involves a reversible reaction, and as the time passes, we will see no appreciable dissociation. So as compared to the initial concentration of ammonia, the ion concentrations formed will be much less in the case of a weak base. So this is actually the end of the presentation. If we summarize, what did we cover in this presentation? We learned acids and base properties, we classified them, and we also investigated their dissociation with strong acids and strong bases, and also we compared the ionization extents of acids and bases. So this is the end of this presentation. Let's meet in another lecture. Thank you.